Hi everyone, I'm Brendan and my project is on peer-to-peer federated learning. In this project, we will be looking at designing an algorithm to make the best decision in maximizing communication efficiencies. Federated learning was introduced by Google in 2017 to improve keyboard text prediction. Today, we see it in most phones and even in healthcare to address data protection concerns. The field generally holds three key assumptions. Firstly, the field runs in a privacy-focused setting. Just as in text prediction and in healthcare, it is morally and legally wrong to store and transfer personal data of users without consent. Federated learning helps us bridge this gap by sharing what we learn instead of what we learn from. As such, there has been extensive development in privacy-preserving methods in weight sharing. Secondly, clients will be non-identically and independently distributed. One person's texting patterns may be very different from another. It may also be in a whole nother language. This gives rise to the next assumption that there is expected to be local and global patterns. How most people text is largely similar, but there are some individual characteristics as well. This is also true in healthcare when comparing globally to regionally. To address this, the field has expanded from a client-server architecture to a hierarchical and a peer-to-peer one. However, we began asking the question, what happens if we were to relax the privacy constraints within trusted peers? One paper sparks this idea. In 2018, Zhang and his team at ARM showed that accuracy can fall by up to 55% on highly skewed non-IID data. They observed the accuracy can be increased by 30% for the CIFAR-10 dataset with only a 5% global shared data. However, with the strong focus on privacy in federated learning, most developments move towards weight privacy. This project seeks to further this discussion on loosening data sharing rules and explore scenarios where the two algorithms may perform better in. The output is an algorithm to maximize inference accuracies while minimizing communication costs. To support the experiments, we explored a novel VAE architecture to support conditional inferencing and sampling. Using variational autoencoders allows us to provide some level of anonymity with reduced data quality. Furthermore, the conditional sampling allows us to sample within data points and maintain patterns rather than reconstructing a private data. We tested a Gaussian latent space with VAE and a discrete latent space with VQ-VAEs. We chose conditional VAE due to its added conditional sampling ability and simplicity over conditional VQ-VAE. Our base experiment looks to identify which parameters leads to the best improvement in train and test accuracies through an exhaustive search. We control and induce various skews into our datasets through the actions above in the table. These feed into the larger system to test in various dataset distributions, number of clients, ratio of data across clients, size of network, levels of training in the network, and the amount of training in each client before communication. We learned that data sharing gives the highest accuracy but lengthens local training times. It should be performed with spare local compute availability. We also learned that synthetic data is significantly better than just sending raw private data. It is also effective in accounting for shifts in non-IID clients. Hence, synthetic data should always be sent instead of private data. Federated averaging has an averaging effect on the expected accuracy. We should always run it if the peer has a higher accuracy, as weights are often smaller than data. Lastly, we should send data when a class label is missing locally. This translates to a decision tree on our right, where the action that we will believe will maximize the inference accuracy with the least bandwidth cost. To validate the algorithm, we ran an 8-node setup with a pre-trained VGG16 backbone. The connections are shown on the left. The dataset sizes are even across clients with a non-IID distribution. The baseline only runs federated averaging every cycle, and the results are shown on the right. There is a significant improvement or similar improvement on top of just running federated averaging. This is observed in 6 out of the 8 nodes tested, except for the last 2 nodes, G and H. Further minor tweaks can be done to fine-tune the algorithm further. In conclusion, an algorithm to maximize inference accuracy given a communication constraint is proposed. It is effective as it shows an improvement above simply running federated learning. Thank you for listening to my presentation.